We start with a coordinate system, an x-axis, y-axis and a z-axis. This has been set up by an observer. Let's call this person A. A wants to describe the world in terms of this coordinate system. So A might be looking at a particle which is moving, and at some instant of time will describe the position of the particle by coordinates x, y and z as measured using these axes. Now we are assuming that these axes are at rest with respect to A. Now we define the position vector of this particle at some instant of time as the vector from the origin of the coordinate system to its location. The position vector is usually described using the letter R. As you can see, in terms of its components, R is nothing but x I cap plus y j cap plus z k cap. Now as the particle moves around, x, y and z change. X is a function of time, y is a function of time, and z is a function of time. Just to give you an example, I will write down the position of a certain particle might look like this. X is a function of time, that might be 3t I cap, plus y is another function of time, maybe it is t squared j cap, and z maybe, well, let's take it as, what shall we take it as? T cube, why not? K cap. I'm just doing an example. So at time t equal to 0, the position vector or the position of the particle is 0i plus 0j plus 0k. The particle happens to be passing through the origin of this coordinate system at time t equal to 0. At time t is equal to 1, its position is 3i plus j plus k. At time t is equal to 2, its position is 6i plus 4j plus 8k and so forth. So we know the position of the particle at every instant of time, which means its entire motion is completely described by this function. When you give the position vector as a function of time, that's a complete description of the motion. All the other particles' properties, for example, its velocity, acceleration, momentum, kinetic energy, angular momentum, everything can be derived from this function. Its velocity at any instant of time is defined as rate of change of the position, in other words, rate of change of the position vector. And for our example, this becomes, differentiate this with respect to time, and keep in mind that the vectors I, j and k, the three unit vectors, they are not changing with time. They are constants. So it becomes 3i cap plus 2t j cap plus 3t squared k cap. So now we have the velocity at every instant of time. For example, at time t equal to 0, the velocity is 3i cap. So now we know that at time t equal to 0, it's passing through the origin, moving in the positive x direction with a velocity of 3. And if we're using SI units, that's probably 3 meters per second. Let's stick to SI units. So now we know the velocity at each instant of time. For example, at time t is equal to 2, at that instant, the velocity is 3i plus 4j plus 12k. Meters per second. We can also find its acceleration at every instant of time by differentiating the velocity, because we define the acceleration as the rate of change of velocity. In this case, how do we implement it? By finding the rate of change of the velocity vector. 3 is a constant. The first term is 0, the derivative. The second term is 2j cap plus 6t k cap. As you can see, the acceleration is a function of time and it's not a constant function of time. The acceleration is not constant, it is changing with time. If I want to find the momentum of the particle as a function of time, I just have to multiply this velocity by the mass of the particle. I will get the momentum as a function of time. What about the kinetic energy? The kinetic energy is defined as half mv squared, but then I have the velocity as a vector, so this is nothing but half m v dot v, the dot product. Because v dot v is nothing but v times cos 0, that's the angle between v and itself. Cos 0 is 1, it simply becomes v squared. And from the properties of dot products, we can write it as half m. V dot v becomes vx times vx squared plus vy squared plus vz squared. In our example, it's going to be 9. I'm squaring this, vx squared plus vy squared 4t squared plus vz squared 9t power 4, and don't forget we have to multiply this by half m, and there are no i's, j's and k's here. This is just a number which is changing with time. That's the kinetic energy as a function of time. Let's just pause for a moment and think about it. Why is the kinetic energy of the particle changing? That's probably because external forces are doing work on the particle.